Physical properties like area, volume, and temperature are scalars, since we only need a number to represent them. But when we deal with other properties such as velocity and acceleration, we may use both a size and a direction. Such objects which have a direction and a size or magnitude are called vectors. For example, if we move an object in some direction with a force, we describe that force as a vector, or if we're moving with constant velocity. Assume that we are moving from point A to point B, and our velocity is 5. It means that our vector has a magnitude of 5 and an AB direction. We denote the vector from A to B as AB, or we can just name it with one of the lowercase letters, but also including an arrow or a line on the top. For example, A. We call B a head and A a tail. The length of that segment is our vector's magnitude. You may say, hey, but it's just a line segment with an arrow. And you would be almost right. The difference is that we can move the vector and it will remain unchanged, but not the line segment. These three vectors, for example, are identical because they have equal magnitude and the same direction. So what can we do with vectors? Let's put this one on a coordinate plane. We can put it anywhere, but for now, let's move it so that its tail has coordinates 0, 0. If the coordinates of the tail A are 0, 0, then the coordinates of the vector AB are coordinates of its head B. Easy! Our vector is now just two numbers, the coordinates of the head. Assume that B has the coordinates 4, 3. Then AB equals the square root of 4 squared plus 3 squared, which is equal to 5, and that we know because of the Pythagoras theorem. Generally speaking, if vector AB has coordinates xy, then its magnitude can be found using this formula. We can even add vectors. Imagine that you are pulled by two forces, F1 and F2, at the same time. Which direction will you move in? Let's force ourselves step by step. Let's allow F1 to do it first, and then F2. We do that by moving F2 in such a way that its tail becomes attached to the head of F1. Then we connect the tail of F1 and the head of F2. The vector formed is the sum of F1 and F2. Another method would be to put the tails of the two vectors together and draw a parallelogram, like this. The diagonal vector that starts from the tails of F1 and F2 will be the sum of these vectors. We can also just add corresponding coordinates of two vectors and get the coordinates of the sum vector. For example, if we have vectors A with coordinates 5, 3 and B with coordinates 2, 4, then C equals A plus B, and so we have the coordinates of vector C as 5 plus 2, 3 plus 4, which is 7, 7. We can also multiply a vector by a number. If the number is positive, the direction will remain the same, and the magnitude will be multiplied by this number. If the number is negative, we change the direction of the vector to opposite, and then multiply the magnitude, or just multiply both coordinates by that number. If vector A has coordinates xy, then vector n times A will have coordinates nx and ny. To find vector A minus vector B, just multiply B by -1, which changes its direction to opposite, and add. We already know how to add vectors. Now let's use this new knowledge. There are two vectors, vector A with coordinates -3, -1, and vector B with coordinates 1, -2. Find this vector and its magnitude. We can analyze it even without drawing, as it is one of the features of vectors we already know. First, we find the coordinates of vector -2b. Then the coordinates of vector A minus 2b. And finally, the magnitude of this vector. Pretty easy, isn't it? We simply completed the same operation with each of the coordinates. Now let's look at what happened on the coordinate plane. First, we found vector negative 2b. Then we added vector a and vector negative 2b. After that, we used the Pythagoras theorem to find the length of that vector. Can you find the coordinates and the magnitude of this vector? Vectors a and b have the same coordinates as in the previous task. Pause the video and give it a go. Vector negative 2a plus 3b has coordinates 9 and negative 4. And its length is the square root of 97. Did you get it right?